Okay, so next we're going to see a problem from computational geometry, and let me call this as slopes problem. Okay, so the input is going to be given a set of n points in 2D. What I want to find out are the following things. First, I want to find the pair of points such that the slope of the line segment between them is the maximum. So this is our first question. So essentially, if these are the points, okay, n points, that means I can draw a line between any 2 points like this, okay, like this. So basically, if there are n points, I can draw up to n choose 2, that is big of n square number of line segments. Okay, this many line segments, and what I want to know is, among these n square line segment, which one has the maximum slope? That is the first question. The second question is similar. Again, I want to find the pair of points such that the slope of the line segment between them is, instead of maximum, now I want to find the minimum. Okay, that is the second question. And the third question is, I want to count the number of line segments with slope between, let's say, alpha and beta, where alpha and beta are given as a part of the question. So I give you a range, and I want to find, basically I want to count the number of line segments whose slope is between alpha and beta. So these are the 3 questions I need to answer, and let's see how to deal with it. All right. So if you haven't seen this question before, I strongly recommend you to try them first. At least the first 2 questions are relatively easy. The last question is slightly more involved, and it has a very nice solution. Actually, I took this question from this textbook. It's on computational geometry. All right, so let's go ahead and solve them. All right, let me just show how to solve the first 2 questions. The solution is relatively simple. Okay, so here is what I'm going to do to solve question number 1 and 2. Okay, solutions. What I'm going to do is this. First, I will sort all points with respect to x coordinate. Okay, basically I arrange all the points in the ascending order of x coordinates. Let's say the points are, like, after this sorting, suppose the points are P1, P2, P3, P4, etc. up to Pn. Next, what I'm going to do is this. I'll take every pair of consecutive points and I try to find the slope between them. okay, the slope of the line between points P1 and P2. Okay, so before that, what is the definition of a slope? So if we have, let's say if you have 2 points, let's say A, B and C, D, right? The slope is what? The slope is this height divided by this length. So slope is this height divided by this length, and this height is what? B minus D divided by this length is A minus C. Okay, so given 2 points, we can compute that corresponding slope in constant time. Okay, so coming back to our algorithm, I'll take the first pair, compute its slope. So let me call this slope as, let's say, M1 or maybe M12. Then I will take the second pair and compute their slope, that is, let's say, M23. I'll put a comma in between, 2, 3. Then I will compute between 0.3 and 0.4. So that is 3, 4. So I'm just using a notation something like Mij for the slope between Pi and Pj. And finally at the end I will have n minus 1 comma n. So essentially I have computed n minus 1 number of slopes. And here is what my claim. The minimum slope is going to be the minimum among these n minus 1 values, and the maximum slope is going to be the maximum among these n minus 1 values. Alright, so if this claim is true, then what I can say is this algorithm will take only n log n time, right? Because you need to do one sorting, that is n log n, and after that it just computing n minus 1 number of slopes, right? Or linear number of slopes, and picking the min and the max. So overall the whole thing can be solved in n log n time. So n log n is the running time, right? The naive running time is n square because there are n square pairs, and if you naively do this, that is big O of n square, but suddenly we are able to bring it down to n log n. Great, but now I need to prove that why is my claim true, right? So essentially what I have done is, instead of computing the slopes between every pair of points, I just did only between consecutive pairs. So somehow I want to prove that the minimum slope and the maximum slope are going to be one among the slope corresponding to two consecutive numbers. And for that so let's go ahead and prove it. So let's go ahead and prove. For that, what I'm going to do is, I'm going to take 2 points, let's say Pi, and another point, let's say Pj, such that Pi and Pj are not consecutive, okay? Not consecutive, which means j is strictly greater than I plus 1. That means there is at least one point between them, right? Between them in the x coordinate sense. Okay, so now let me draw a line between Pi and Pj, and what I want to show you is this. During the computation of this minimum slope and the maximum slope, I don't have to really worry about the slope of this line. That's all I need to prove, okay? And the way I'm going to prove is this. Suppose Pi and Pj are like this, okay? And there is going to be at least one point between them, and that one point could be, with respect to this line, that one point could be above this line, or it could be below this line, or it could be on this line. These are the 3 possible scenarios, right? And if there is a point above this line, then what is going to happen is, I mean, there has to be a point between them, and if suppose that point is above this line, then there is going to be a line segment like this, and there is going to be another line segment like this. And if you look carefully, the slope of this line is more than the slope of this line, right? Therefore, this Pij, the line between I and j, can never be the max. On the other hand, this line in fact has a negative slope, right? I mean, that depends on where this point will be, but in general, this point is going to have a slope lesser than the slope of this line. Therefore, this line, this black line, can never be the one with the minimum slope, which means the slope of the line between I and j is irrelevant during the computation of min and max. Similarly, if this point is here, you can draw a line like this, okay? And if you look here, this line is like below this line, so the slope of this line is going to be lesser than the slope of black line. Therefore, this can never be the minimum, right? This can never be the minimum. Similarly, this line has a slope more than this one. This is more steep, right? Therefore, this can never be the maximum, right? So in this case, in both these cases, this line can never be the min or the max. Now, what happens if the middle point is on the line? If the middle point is on the line, then the slope of the main line is the same as the slope of, the line from this point to the middle point. Even in that case, we don't have to really worry about the slope between Pi and Pj, because there is another candidate. There is another line segment with a shorter length, right? With a shorter length. That means between two closer points, right? And that closer point might have again another point between them, and that point might get into one of these three cases, and suppose even in that case, if it is like this, the middle case, then you will find another pair of points with the same slope which are even closer. So eventually you will find closer points, and how far you can go until you are really close, that is 2 consecutive points. Okay? So in summary, when you have 2 points Pi and Pj, not consecutive, right? And Pi is below Pj in terms of y coordinates, then we don't have to worry about the slope between Pi and Pj. So another scenario is, in this figure, if you see Pi is below Pj, so what could happen is, Pi could be here and Pj could be here. Pj could be here. Here again, you can have a look at 3 different scenarios, like, the middle point can be in one of these 3 cases, and you can again draw some lines and convince yourself that even in this case, we don't have to worry about the slope of the line between Pi and Pj. And one more case is, here Pi is below Pj, here Pi is above Pj. The last case is Pi and Pj can be, at the same level. Again, there could be some point like this, and you can draw some lines and convince yourself that, we don't have to worry about this. Okay, so this is kind of like a proof, I would say a proof sketch. Right? It's not so rigorous, but kind of like a proof by picture, but it is sufficient for our purpose. All right, so this was relatively easy. Now let's get into the last portion. That is basically counting the number of lines with slope between. We want to count the number of line segments with slope between alpha and beta, some given alpha and beta. so let's go ahead and see the solution. What I'm going to do is this. Corresponding to each point AB in my input set, I'm going to define a line like this. Y is equal to AX minus B. Okay? For each point in my input set, I have defined a line like this. And why I am doing this, it will be clear pretty soon. Therefore, if I have another point, let's say CD, then the line corresponding to this will be Y is equal to CX minus D. Okay, so my objective is this. I want to kind of somehow, come up with a relation between the slope of the line between these 2 points and something about these 2 lines. Okay, let's see what we can do. The slope M of the line segment between these 2 points is going to be B minus T divided by A minus C. This is the slope, all right? And when I have 2 lines like this, if they are not parallel, they're going to meet somewhere, right? They're going to meet at some point. I don't know when, but as long as they are not parallel, they will meet at some point. And what I'm really interested in is to see what is the x coordinate value of their meeting point, which I can easily solve by equating this equation. The right hand sides of these equations, that is Ax minus B is equal to Cx this is D, Cx minus D, which will be what? X into A minus C is equal to B minus T, or X is equal to B minus T divided by A minus C. Okay, so have a look at this quantity and have a look at this quantity, which are the same. In other words, this point is M. Okay, so what we have now is a simple cute result, that the slope of the line between any 2 points in my input set is going to be the same as the x coordinate value of the point of intersection between the corresponding lines. Okay, so therefore the original problem of counting, my original problem is count the number of slopes between alpha and beta, right? Count the number of slopes between alpha and beta, which I can ask in the same way. Count the number of pairs of lines such that they intersect between, say, 2 lines like this, where x is equal to alpha and y is equal to beta, right? 2 parallel lines parallel to y-axis. So all I need to figure out is count the number of lines after the transformation where the meeting point is within this window. Okay, so how to solve this? For that, let me do something like this. This is my x-axis, and let me first draw 2 lines. X is equal to alpha and x is equal to beta. Now what I'm going to do is, corresponding to each point, I will create the line like this, and let me just draw these lines. Okay, these are the lines. Okay, this much is enough. Okay, I've made a small example where I have 4 lines, and I'm going to number these lines, based on the order in which they have intersected the first line, based on the ascending order in which they have intersected the first line. So I'm going to call this line as the first one, this as the second one, this as the third one, and this as the fourth line. And I want to see which one is intersecting this line first. So that is the second one. Now the second intersection is by the fourth line, the third intersection is by the first line, and the last one is by the third line. Okay, and this is what I'm really interested in. Okay, this quantity 2, 4, 1, 3. All right. So what have I achieved so far? I kind of drew all the lines corresponding to each of these points. Corresponding to each of points, I have got the lines using this transformation. Then I drew all the lines, and I managed to figure out the point of intersection of those lines with this vertical line. And I kind of ranked these lines as 1, 2, 3, 4 based on the ascending order of the y coordinate value of intersection, right? Of intersection with this line. Then I tried to see how is this ordering changes on the other side. All right. So what I want you to do at this point is to have a careful look between, let's say, 2 lines. Okay. Let's say 2 lines. Let's take 3 and 4. The example of 3 and 4. 3 and 4 is clearly meeting within this range. So that means these 2 lines will contribute, these 2 lines, this pair will contribute to the final answer. And here if you see, the order is 3 and 4, the usual order. But if you look at the order of 3 and 4 on the other side, this is 4 comes first and 3 comes second, which is nothing but an inversion. Similarly, 1 and 2 is meeting within this region. So 1 and 2 on the other side is inverted. 2 comes first, 1 comes second. Let's take another 2 lines, let's say 2 and 4. So they are not meeting, right? So they are not meeting. That means their order will stay the same even on the right hand side. All right. So I think the idea is pretty clear at this point. Essentially what? The number of lines, the number of pairs of lines intersecting within this boundary, right, is equivalent to the number of intersections, so equivalent to the number of inversions in this array. All right. So my final answer is simply the number of inversions in this array. And this is an array of size n, and we already know how to compute, how to count the number of inversions in n log n time. So see computing these point of intersections and giving this ranking and everything can be done in n log n time. Mostly you have to do some simple computations and maybe some sorting, right? So the only tricky part is this one, which can be solved in n log n time. Therefore, the whole problem can be solved in n log n time. And that's the solution.